Question 19. It says the acceleration is given by this formula here. Incidentally, the acceleration is minus omega squared x. That's in your formula booklet. That leads on to omega squared is just going to be equal to g over L. We'll use that later on. Show that the time period of the oscillation is given by t squared equals 4 pi. Definition of omega, okay, angular frequency is 2 pi f or 2 pi over t. Therefore, omega squared is going to be 2 pi all squared, which is 4 pi squared over t squared. Oh, sorry, over t. If I rearrange this, I end up with t squared is equal to 4 pi squared over omega squared. Well, we know what omega squared is. Substitute it in here. So t squared is equal to 4 pi squared dividing by g over L, same as multiplying by L over g, so L over g. Done. The student notices that the amplitude decreases over time. Explain this observation. Okay, will it have an effect on t? Well, there is an energy loss. Okay, therefore the amplitude reduces, goes down. There is no effect on t on the time period. Why? Because the time period is independent of the amplitude. We've just shown it in part 1. 2 marks. Part B. Now, with the aid of a labelled diagram, make sure you put a diagram, it asks you to, describe an experiment to test the validity of the equation t squared equals 4 pi squared L over g. Really what you're testing is t squared is going to be proportional to L. 4 pi and g are all constants, so really t is proportional to L is what you're testing. So what equipment? Well, little labelled diagram, make sure you've got a retort stand, you've got some pendulum bob, you want some marker line, okay, so you know that you always start with the same amplitude, the maximum displacement. You need to say there's some way of measuring the length, so you need a ruler. You need some way of measuring the time, so you need stop clock. Then just label your pendulum. Okay. Now, how to get the marks? Describing, so you can now clamp the string. Okay. Use the stop clock. Well, how many times are you going to do oscillations to find t? Maybe with 10 oscillations. It must be more than one oscillation, a number of oscillations. Use a ruler to measure L, the length. There we go. There's L. Then you're going to vary the length and find t. So there's your method. How are you going to make sure it's valid? You're going to use small oscillations. Okay, you could say maybe less than 10 degrees or something like that. Okay, you need a sort of start-stop marker. It's a start marker. Sometimes they call this a fiducial marker. Fiducial, but some sort of marker. so you know you start at the same point each time. And you're going to time for maybe 10 times 10 oscillations, and you're going to start and stop at the same point. You could say the middle, you could say from the marker. So your analysis, well, how are you going to prove? There's 2 or 3 ways. You could plot a graph of t squared against L. If you plotted a graph of t squared against L, okay, if it's proportional, if t squared is proportional to L, what are we going to get? It's going to be a straight line. It must be, this is important, through the origin. Don't just put a straight line, it must be through the origin if it's directly proportional. You could of course just say, you could use the table as the results to work out t squared over L and see if that's a constant. Again, that would be an acceptable method. What is the gradient of this line? Well, using your formula, the gradient simply be 4 pi squared over g. Okay, part C. Similar experiment. Each tick corresponds to half a period. Show that the length of the pendulum is about, for a tick of 0.1, is about 1 meter. Well, if the tick is 1 second, sorry, not 0.11 second, then the time period is going to be 2 times 1. It's going to be 2 seconds. So we're just going to simply substitute the time period t is 2 seconds into the formula 4 pi squared g over L, and if you stick 2 seconds into there, g is a constant, g of course is 9.81 newtons per kilogram on the centre of the surface of the Earth, then that leads around L is going to be equal to about 0.99 meters. 2 marks, should be easy. Make sure you get the correct time period, don't use 1 second. And finally, part 3. If the pendulum were used on the moon, would this clock run faster or slower? Okay, compare it. Don't just say it would be different, you must say it would be faster or slower. Okay, so on the moon G is lower. If G is lower, okay, therefore time period is longer. Okay, and you must justify that using the formula t is proportional, t squared is proportional to L, or really that's t squared is 4 pi squared g over L. Okay, if g changes, g reduces, t increases.